So the properties of waves. So we're going to be going over some simple concepts that you guys have looked at in CSEC, right? And then look at all the general properties of waves that we can understand at the basic level, right? So first of all, we need to understand the key terms that we're going to be used to describe wave behavior, right? So displacement is the first one. So displacement in the context of waves is the distance of a particle from the in the medium, right? The distance it moves from equilibrium, right? Due to the fact of the matter being that we did simple harmonic motion, we already know that the displacement, right, is going to be any distance, right? So for example, let's use this dotted line. Any distance here is going to be the displacement, right? So displacement, let's say x1, displacement x2, any displacement here. But the maximum displacement we know is the amplitude, all right? So that's displacement. For the amplitude, we know now we know that that is the actually maximum displacement, right? So this is a lot of rinsing and washing information that we just did, all right? So we know that we have the amplitude there, which is the maximum displacement, right? Go ahead. All right. Is that okay? All right, no problem. So the amplitude we know is the maximum displacement, right? And we can also look at a relationship between, well, on these graphs specifically, where we can get twice the amplitude, right? If we move from up here, which is a crest, right, to a trough, right? So from crest to equilibrium or trough to equilibrium is the amplitude. But from a crest to a trough, as we see here, is twice the amplitude, which makes sense. It should make a lot of sense, right? Which makes sense. All right, so that's how we interpret the amplitude there. Moving on. The period now. We know that we're looking at the displacement time curve when we're describing the period on the diagram, right? It's the time it takes for a full oscillation, right? So the oscillation, right, we can look at from the waves at equilibrium to equilibrium here, right? That is one full oscillation, and the time it takes for that one full oscillation is going to be described as the period, right? The period is defined as t, right? Is equal to the inverse of the frequency, or 1 over f. There's also lambda over v, where lambda is the wavelength, right? Divided by the velocity. Okay? So looking at that. The frequency can also be determined from this diagram, where we have the amount of wavelengths passed through in a second, and we're going to be looking at the frequency in its own slide. Alright, so that's the period. The wavelength now, right, is measured in meters, of course, right? It is the distance between successive crests or successive troughs, right? So for example, between two successive crests is one wavelength. The distance between two successive troughs, however, is another wavelength, right? And this is measured in meters, of course, right? It could be nanometers, it could be picometers, it could be femtometers. But as long as it is in meters, all right? So we have that there. That's the wavelength. The distance between two crests or the distance between two troughs, all right? But it could be the distance between any two successive points as well, right? Because I could take the wavelength to be this. This is not a wave, this is not a crest or a trough, but it is from this point back to the same point. So this is a wavelength as well. Period versus the wavelength now. Period, right, is described visually in the same way a wavelength is described. But the only difference is that this is a time displacement and this is a distance displacement, right? There's a difference. So the time displacement between crest to crest is period, between trough to trough is period. When we're talking about distance, no, between crest to crest is period, between trough to trough is wavelength, right? And between trough to trough is wavelength, right? So the only difference between them is that one is a displacement time, and the other is a, well, displacement distance. All right, so we have that there. So we just need to note that, and probably this is very obvious, but I'm just going through it for its sake. Alrighty, the frequency, the frequency is the number of wave cycles that pass at a given point per second, or pass through a given point per second. We know it's measured in hertz, and it is the inverse. It is inversely related to the period, right? Because if the period is t is equal to 1 over f, then f is equal to 1 over t, right? So we have that there. So a low frequency will be described as having a longer wavelength, right? And a higher frequency will be described as having a shorter wavelength, right? How it looks there. So now frequency, we have three different definitions: 1 over t, v over lambda, or omega over 2 pi. Three different equations, right? So don't say you can't calculate the frequency if you don't have the period. Nonsense, right? You can calculate the frequency from other means. All right, so looking at that, we should be able to understand how that works. Alrighty, and this equation we got from simple harmonic motion. We got that equation from the other PowerPoint before this. All right, so we have that there. We also have other equations. The energy associated with the wave E is equal to h, which is Planck's constant, times the frequency. Or it's equal to Planck's constant times the speed of light over the wavelength. We're going to be speaking about things like this a little bit more in depth when we go into unit 2, right? But for right now, this is the energy relation equation here, right? Persons who do chemistry have done it in unit 1 chemistry as well. Alrighty, so let's have a look now. Velocity now. Wave velocity is the speed at which the wave propagates through a medium, right? So how fast can light travel through a vacuum? How fast can sound travel through air? So that's what we're talking about, right? The speed at which a wave propagates through a medium, right? It's given by the equation v is equal to frequency times the wavelength. Or for a spring, it is omega divided by k. Or for a pendulum, right, it is the wavelength divided by the period, right? Or, well, not really for the pendulum only, but it could be pendulum and spring. But definitely this with the k is for the spring, right? Looking at relation to a spring. But we're more than likely going to use f times lambda or lambda over t to find the velocity, right, of a wave. However, for a wave on a string or a cord, right, for a string or a cord, v is equal to the square root of the tension divided by mu, right? And mu is defined by the mass divided by the length of the string. That is what we're talking about there. So if we're talking about a spring or a cord and we're trying to find how fast do the waves on a spring or a cord propagate, v is equal to the square root of the tension divided by mu. Alright? Which is the mass length ratio, which is mass over length. Alright? So we're looking at that. But more than likely, we are going to be focusing on this velocity equation over here. Alrighty? So looking at how fast a wave is traveling. Transverse versus longitudinal waves. Now, we should be able to understand the difference between the mechanics of a transverse wave and the mechanics of a longitudinal. Alright. Alrighty. So transverse is a longitudinal, right? Everybody here has done I assume that everybody here has done CSEC physics, and that everybody knows the difference between transverse and longitudinal waves, right? Does everybody know the difference between them? As long as we know the difference between them, lovely. All right. So since we know, then we can run through this part, right? Not gonna zoom through it though. Well, let's look at this, right? So we know that the mechanical waves are disturbances that travel through a medium, solid, liquid, gas, right, or gas, transferring energy from one point to another. Those are what waves are, right? They are disturbances traveling through media that transfer energy from one point to another without transporting matter. These waves can be classified as two main ones, longitudinal and transverse. Transverse waves, what are the characteristics of these waves, right? We're looking, for example, a wave traveling along a string is an example of a transverse wave, where we have perpendicular motion. The particle displacement is at right angles to the direction of the wave traveling, right? So we have the particle being displaced up and down, and that is at 90-degree angles, right, to the direction of movement. Alrighty? So we'll have the components of a transverse wave. We have a crest, we have a trough, right? So the crest is the highest point of the wave, or the positive amplitude, and the trough is the lowest point of the wave, or the negative amplitude. So positive amplitude is the crest, negative amplitude is the trough. Examples of these waves are like water waves, light waves, and string vibrations. Right? So it's the movement of the particles in the medium. Right? So this is how the the transverse wave comes about, right? The particle motion, right? So in transverse waves, particles of the medium rather oscillate perpendicular to the direction of the wave propagation, right? So that tells us that this is a transverse wave. If a wave travels horizontally along a string, the particles of the string must move up and down. So if you did that experiment in CSEC or still in CAPE, right, you need to move a string up and down in order to allow it to oscillate and produce a wave. Alright? So each particle moves from equilibrium, right? So if we draw a line through this and call that the equilibrium line where x is equal to 0, we see we're moving above, right, and below equilibrium. So we have a positive amplitude and a negative amplitude. Alright? So let's move onwards. Longitudinal waves now, right? They have parallel motion. So the particle displacement is in the same direction as the wave travel. But we do not have crests and we do not have troughs. We have compressions and rarefactions, right? So we have compressions where the particles are close together, right? So here are compressions, for example, in a slinky or a spring. And then we have rarefactions, right, where they are spaced out. Examples of these types of waves are sound waves, seismic P waves in earthquakes, and spring oscillations. This is a movement of the particles in the longitudinal waves. Alright? So we know that the particles oscillate in the medium parallel to the direction of the wave propagation. Right? It creates regions of compression and regions of rarefaction, right? So compression when the particles are close together, rarefaction when the particles are spread apart. Alrighty? So that is that. So we can see the wave moving across with the compression and the rarefaction. Alrighty? So looking at stuff like this now. Alright? So hold on. Before I begin this experiment, let me just check something real quick. Alright, so this is just an experiment to look at the waves themselves, right? Just looking at generally waves and looking at how they're produced, for example, in this with the water wave here, right? So this is a transverse wave, and we can see the diagram like this with the water level, etc. Right? So that's a transverse wave, and we can see how it moves here, right? Can also have the sound wave, right? So let's go back to the water wave first. We want to look at the particles right here specifically, right? I don't think we can see the particles here, but it's fine. Right, so we understand that we have crests and troughs. So where it is blue, it's a crest. Where it's dark or black, there's a trough, right? With the sound waves now, we can see that the movement of particles and how we have compressions and rarefactions, right? So we should be able to understand that. So we can see the compression and the rarefaction for the longitudinal sound waves. Alrighty? Any questions or concerns before we move on? Any questions or concerns? We're all good. Alrighty. The next concept has to do with polarization. Polarization really refers to the orientation of the oscillation, right? So light is an electromagnetic wave. Light contains oscillations in the electric. Okay, I don't want to make it so simple that it doesn't make any more sense or make it too complex, right? But we know that light is an interaction of the interference within the electric field and the magnetic field, right? That's how it creates oscillations in both fields to produce an electromagnetic wave, right? So we can actually isolate one of those waves, right? We can actually isolate it, and that isolation is what we call the polarization. Now, longitudinal waves such as sound waves cannot be polarized. Therefore, when we look at polarization, we're only looking at transverse waves. All right. So we have linear polarization where the wave oscillates in a single plane. For example, light waves in an electric field oscillate vertically. Right? So the wave that is produced is vertically polarized. Right? For example, in this case. So all of that noise and unpolarized light is now reduced to one directional or unidirectional light. That is linear polarization. We have one plane of oscillation, right? And that is the polarization of light there. Alrighty. So it's because of its angle as well, because it has angles with it. Lovely. Alright. We also have something called circular polarization, right? The electric field rotates in a circular motion as the wave will propagate. And this occurs at two perpendicular components of the wave having equal amplitude but a phase difference of 90 degrees. So we end up with this circular one now. The circular polarization here. So you have different types of polarization. So in A we see the 290 degrees as the waves move in the phase difference. And we're going to talk about phases a little bit later. Probably a little bit before, a little bit after the break. Right? So we have that circular motion now. Alright, of polarization. We also have elliptical polarization, right? Where it's not circular, but just in a squashed or an ellipse, right? So a squashed circle or an ellipsis, right? So we have that difference now. So it's just a shape. That's the only difference between them. Alright? So we have this here now, right? So the difference between the linear polarization, circular polarization, and elliptical polarization, right? And we have right-hand polarization and left-hand polarization, but I'm pretty sure that the syllabus does not intend for us to go any further at all. If we go further, there's math to be seen, alright? But we won't. So linear polarization, so we understand that, right? So we can look at the mechanisms of polarization. For example, natural polarization. Light becomes polarized, partially polarized, when it reflects off of surfaces like water or glass, right? So some of the orientations of the electric field are partially absorbed and some are reflected. For example, when we describe the deep blue sea, right? Technically, if light is shining through water, we should be able to see the bottom of the ocean at all times, yes? Isn't that true? Should be able to see the bottom of the ocean at all times. but the light will absorb some orientations of the electromagnetic wave that we call light, right? And the absorption of light leads to a darker color. For example, objects are black because they absorb the most amount of light possible for them. So that's why the surface of the ocean is perceived as much darker, right? And it reflects what light it can into the atmosphere, and that light tends to be within the blue region. Skies are blue, right? Like that, right? Skies are blue because of other reasons as well, but we're just dumbing it down to only polarization, right? Because we're talking about polarization, right? So we just have that there for natural polarization. But we also have artificial polarization, for example, in polarized filters. These are materials that allow only light waves with specific orientation of the electric field to pass through, commonly used in sunglasses to reduce glare as well. Right? So for example, when we put on polarized lenses onto cameras and we change the color or the heat, right? So we want a hot, warm colors or cool colors, right? We start to block out different types of colors within those spectrum, with those spectra rather, right? So you want to block out, you want to allow a photo to appear cooler, we'll block out the reds and oranges and stuff like that with blue, right? And if you want it to appear warmer, we'll block out the violets and the greens and the blues for it to appear more, warm, right? So that's what we do with polarization. We also have something called birefringence, right? Where materials like calcite will which have different refractive indexes or indices, right? For light polarized in different directions. So it will actually cause like a mirroring effect. But we're going to talk more about that refraction and stuff like that when we reach optics, right? When we discuss optics. Some more examples of polarization, for example, polarized sunglasses that allows it to reduce glare. We actually polarize to emit information, right, through TV antennas and radio signals, right? So we don't want all of the waves of light to be interacting with these devices, so we polarize them. Broadcasting can be polarized. For example, TV antennas are designed to receive either vertically or horizontally polarized signals, right? Those are the only ones that they will accept. And you can think of polarization in terms of, different types of mathematical analysis, where we have AM waves, as in AM radio, and PM waves, as in PM radio. But we won't talk about stuff like that until module 2. Not module 2, unit 2. Right? Optical devices now, right? So polarization is used in optical devices such as microscopes to enhance the contrast and reduce reflections. So polarizers are always in microscopes as well to allow us to better visualize organisms or different artifacts within cells. Right? And artifacts are the dead material. Let me not go back too far into biology unit 1. But yeah, so we also have 3D movies as well. We use polarization in the 3D glasses, right, to allow for these images to create a stereoscopic effect for them to come alive. Alright, so polarization is used a lot of times or a lot of places, right, that we normally would interact with. Alrighty. So the intensity of a wave is different now. So it's moving from polarization to intensity. Is everything okay so far, everyone? Any questions or concerns? Alrighty, everybody's okay. It seems like this information is like much easier than simple harmonic motion. It's just okay, that's how it works. Okay, that's fine. Like it seems like it's just more digestible. Alright. But let's look at this intensity of a wave now. The relationship between the intensity of a wave and its amplitude is fundamental to the understanding of how the energy of the wave is distributed. Now, the reason why I'm reading the lines, because some person may be bothered about that. The reason why I'm reading lines is because I sat down and I wrote these sentences. So I was like, okay, instead of putting it in a script, let me just put it on screen. Right? So I have that there. So there's a relationship between the intensity of a wave and its amplitude. It's very important understanding what an intensity is. Intensity is really the power transmitted per unit area, right? And the power is defined in this relationship, right? Where Intensity I is equal to the power P divided by the area A. Therefore, what is the equation for power? Anybody? Power is equal to what? Or IA, which some persons have not completed, but it will start being marked and received in February to March. Right, so P is equal to IA. Right, so we have that there are AI. Right, so we could have something like that. Right, so we're looking at something like that. That should be fine. So it times by A over here, so it times by A over here. Therefore, P is equal to AI or whatever. Alright, so lovely. That's a power. Power AIT, that's crazy. Alright, but power is equal to AI or IA. Lovely. So amplitude and energy in waves now. So the amplitude of a wave is the maximum displacement. We've been rinsing that over and over again. Okay, nobody should forget what an amplitude is. Impossible to forget it. Right? And the energy created by a wave is directly related to the square of its amplitude. This is because both kinetic and potential energy in oscillating media increase with the square of the amplitude, right? So the amplitude there, we just have to understand that relationship, right? Between energy and amplitude. I think that's all the syllabus requires us, or that's how I interpret this syllabus wanted us to look at, right? Just the relationship between amplitude and energy. Okay? So we could look at it like that. Right? So we're looking at this, what is this saying? This is simply saying mathematically. Go ahead. This, it's phi, it's what we call, this is cot. This is that trig function. Yeah, trig function. Sine, cos, tan, cosec, cosine, cotan. It's cot. It's an example. It's a function, right? All right, but really and truly, what I want to get to is just this. This is what this slide meant. I put this equation here to show the full wave equations and what they can look like, right? So yeah, cotangent. I see people not doing pure maths, But yeah, all right. So we have something like that. So the energy of a wave system is directly proportional to the amplitude squared. This is just something I want you guys to know because the syllabus asks us to look at exactly amplitude and wave energy in systems, and this is the relationship we're looking at. E alpha A squared, right? Energy is directly proportional to the amplitude squared. Moving on, intensity amplitude relationship, right? We can also look at this, the intensity now, where E is directly proportional to the A squared, I is directly proportional to A. Right? So we can see here now the intensity and the amplitude on one graph. Alrighty? So as the intensity increases, the amplitude increases. As the amplitude decreases, the intensity would decrease. Are we understanding there? And for persons doing unit 2 or who did unit 2, this is what amplifiers do. They increase the intensity of the wave and we increase the amplitude. We'll discuss that in module 2 of unit 2 physics. Alright? Not me saying this as if I'm going to be doing this tutoring till next year, but it's fine. So let's look at this, right? So we're going through this, right? That is what's happening here. That's the relationship. So this means that the amplitude, right, of a wave doubles, right, as its intensity increases by a factor. Hold on. There's something wrong here. There's something wrong with the intensity relationship here. Can anybody describe what is the issue here? There's something very wrong here. Nobody sees it. You know, I wish somebody saw it. This should be squared as well. Right? There was something wrong with this. Because once I realized that the intensity increased by a factor of 4, no man, it must be a squared. Right? So there's a typo in the PowerPoint. My bad. Right? So if I send the PowerPoint, I need to remind you guys that that should be squared. But intensity should be proportional to the amplitude squared. Or I is equal to Ka squared if we use a proportionality constant. Alright? So that must make it easier for you guys to remember, right? Or to study. Amplitude and energy and amplitude and intensity, same relationship. E is directly proportional to A squared and I is directly proportional to A squared. Alrighty? Phase and phase differences now in waves. A phase just speaks to its position, right, at a point within one cycle, wave cycle, right? So it is normally expressed in terms of radians. Therefore, I would love for when we start going through some calculations, our calculator must be in radians. Okay, my bad. I should have expressed before. You see all those simple harmonic equations? If your calculator is in degrees, all the answers are wrong. For the most part. It depends. And when we do past papers, I'm going to explain to you when we need to use radians and when we need to use degrees. But not for now, we're going to be focusing on the fact that angles are expressed in degrees and or radians. We're going to be looking at when. Right? So it's important to actually do the question so you can see, okay, when do I use radian, when do I use degree? Alright? But yeah, so usually we're going to be working with the radians naturally. So it indicates where the particle is right within the oscillations at a particular time. Right? For example, these two waves are in phase, meaning that at any point in time the particles are exactly upon each other. But these waves are out of phase, the pink and the purple, right? Are out of phase slightly. But we can see that the last ones are completely out of phase, where the amplitudes match up, and it's not supposed to be that way. Alright? So we notice that there's a distance between the two. There's a distance that is separating, right, them with the phases. Go ahead. This? This, this is what we call a phase constant. Phase constant. The gravitational potential energy symbol. It could be. It could be. Yeah, it could be. Right? It depends on which textbook uses it, Right? It depends. Oh, it's not the same thing. No. It's not the same thing. No. It's like how x is this, the phase constant, right? It describes the position of the particle. It describes the phase, like how the phase is set up in a wave, right? That's what it generally does. Okay, so I'm going to give you exactly what the phase constant does, but I know that phase constant is not used in the syllabus, but do you still want to write it? So the phase constant is a value that describes the phase of a wave. The thing is that it has multiple meanings, but we just have that, alright? So it would have described, nah, no, we don't use that gravitational potential, right? So it's the same way how x is displacement, x is also distance, x is also extension, right? X is so many things, right? But we still use the symbol x. Yeah. Oh, that's fine. Okay. Yeah, it is used there actually. But in the context of waves, it's a phase constant. Okay. No. All right. Lovely, right? So, for example, if we have the sinusoidal waves here, right, we're gonna have its phase being described as, let's say, theta and angle theta, right, as a reference point. If that reference point changes, then the two waves will be out of phase, right? So we have a phase difference occurring, right? So it's a difference between 2 points in a wave or two waves, right, at the same point in space at the same time. So what we're saying, is at the same point in time, this particle is here on this wave, right? This particle is here, but this particle is here. The same particle is here. Therefore, it's just out of phase. It's not directly matching up. And this is what it's saying on this diagram over here, right? This is a difference between the two. That's what we call a phase difference, right? So their maximum and minimum points occur at the same time, right, when they are in phase. But when they're out of phase, their maximum, right, so let me just write this quickly. This maximum here does not occur at the same time as this wave's maximum. So they are out of phase. Hopefully you guys get the gist. All right, when something is in phase or out of phase. So if the phase difference is around a pi radian, right? Pi radians are 180 degrees, then they're completely out of phase, and we meet the term destructive interference. So we're gonna talk about that when we reach interference patterns. We're not gonna touch it right now, but keep phase in mind, right? We'll also have standing versus progressive waves, right? So we have a difference between them. So progressive waves move through the medium, right? So progressive wave, when you think about a normal wave, that's what a progressive wave is. Something moving, right? Carrying energy from one place to another. That's a progressive wave. Just think about that. What we normally call a wave is a progressive wave, right? So I don't want to say, okay, a progressive wave is this and this and that. It's really what a normal wave is, right? But we have something different. We have something called a standing wave that is now different from our regular concepts of waves, right? These are stationary waves that are formed when two waves of the same frequency or amplitude or wavelength travel in opposite direction and start to interfere with each other, right? When two waves are traveling in an opposite direction, the wave does not propagate, it does not move. So they stand in place, and that is what we call a standing wave. The wave does not propagate. The wave stays in one place, moving up and down. And we reach to two important terms, a node and an antinode. A node, right, is a point in a standing wave when there's no oscillation. So basically, where it cuts the x-axis is what we call a node, right? We're looking at that. And where displacement is maximum on the x-axis, we call that an antinode. That's just the difference, right? That's understanding a standing wave. So you have waves that actually don't propagate. For example, right? We're gonna look at an example of a standing wave, right? So we have the amplitude, it varies between 0 at the nodes or maximum at the antinode, right? So amplitude is 0 at the node, amplitude is maximum, right, at the antinode. So I want you guys to piece together these things and have them when you're studying, right? So for example, in this diagram here, right, the node is at 0. The antinode occurs where we have the amplitude and the displacement is maximum, or it is at its amplitude. All right, those are differences now. And the wavelength with respect to nodes now is the distance between two nodes or two antinodes. So the distance between these two antinodes would be the wavelength lambda. The distance between these two nodes here would be the wavelength lambda for a standing wave. All right? Hopefully this makes sense. Let me check the chat now to see if there are any questions that I'm missing. All right. Examples of a standing wave now. Microwaves are standing waves. Literally, exactly. They are standing waves. Microwaves do not propagate anywhere. If they did, then we will have a problem. That's what we call a problem. Right? But no, they don't propagate anywhere. They stay there. Right? So it's a standing wave here. Right? Microwaves in a microwave, right? Or a microwave oven create stationary waves inside the oven cavity, right? And food is placed in areas of maximum amplitude, or the antinode. So have you ever put food in a microwave and only sections of the food, give me one moment for this, right? Only sections of the food heat up, but some sections are cold? The sections of the food that heat up are at the antinode, the maximum amplitude of the standing wave, while the plates are the part of the food that is still cold are actually at the nodes, where the amplitude is 0. So in order to counteract that, microwaves cause the food to spin so that it can actually pass through the antinodes and heat up. Everything has a scientific explanation. Let me read the question. So why not 3 nodes? Because it looks like there's a third node completing the first wave. This wave, there's a third node. Why not? What do you mean by why not 3 nodes? Could you unmute and let me know what you mean by that? Why not 3 nodes? What are you asking? Alright, no problem. Alright, so that's what's happening here. So for a microwave, we have the microwave source, right? We have a probe detector and we have a metal detector, right? So the probe detector is just basically to attach to a meter to figure out, it measures, right, the frequency, the amplitude, those things of the waves, and then we have the reflector that creates a stationary wave. So you see that microwave grating that is on the microwave itself, it keeps it and creates a standing wave within the microwave, right? And notice that the microwave cannot turn on if the door is open, so it prevents stupidity. It prevents stupidity with persons who will open the microwave door and turn on the microwave. So it prevents stupidity by not allowing the microwave to turn on if the door is open, right? So we have that there. Waves on a string now. Strings can have standing waves, right? So string, if both ends of the string, the oscillator and the area where the end of the string is locked, right, or locked in place, right? When you vibrate the string and oscillate it, and we reach a fundamental frequency of vibration, right, along the length of the string, in some periods, it can actually create a standing wave. As you can see, those small diamond patterns on the spring, when you shake it or oscillate it, that is what we call a standing wave. So we end up with nodes and antinodes. So I'm pretty sure you guys have seen this before. You have seen it, right? So we have an oscillator, and at the other end, it is going to be locked in place, right? If you have a string and you hold it in both hands and oscillate it, you should be able to manipulate it and create a standing wave in your very hands. And see where the nodes and antinodes are. All right, those are the waves on a string. We also have resonance waves in open and closed pipes, right? So we have these standing waves in these pipes, right? So on the top we have closed pipes, right? So one end of the pipe is closed and the other end is open. In this case, there's a node at the closed end and an antinode at the open, right? So we have a node at the closed end. Let me show this here. A node at the closed end where displacement is 0, and the antinode at the open end here. Alright? That is 1 full quarter of the wavelength there. Alrighty? Or we could have open pipes. In open pipes now, the node is in the middle and the antinodes are at both ends, right? And if we increase the frequency of the waves, we can note that this remains true. In a closed pipe resonator, we will always have a node at the end, at the one end, the closed end, and an antinode at the open end. The frequency will increase the amount of wavelengths within the same area, of course, because we understand what frequency is, right? But for the open end now, they're open pipes where both ends are open, antinodes will always be at both openings, alright? And then we have now increasing wavelength in between, or increasing frequency in between. Alright? Alright, so this is in, yeah, it is in the syllabus. Alright, so you have the open and closed type resonators. Alright? Now we're finishing up to reach that break, that long break, right? The last thing we have to look at is the practical applications of sound waves in industry. For example, in sonar, right? Now, I am a military person. After I graduate, I will obviously be going off to the military, right? So, sonar is very important to me, right? So, sonar waves, right? Depth. It helps to measure the depth of sea or to detect objects moving at a distance on the surface of the ocean, right? Where we have a ship, we have a transducer and a detector. So what we do is produce the ultrasonic sound waves, pulses, right? We have it reflects off of any object and then it is detected by the detector. So that is how we are able to scan and model the sea floor. For persons who are interested in geology and oceanography and those type of things, we use sonar devices to model the sea floor and to detect objects, right? Or, for example, submarines that are probably currently in the northern Atlantic. But yeah, so we use these devices. That's practical use of sound waves in the industry, right? Another example of sound waves being used is ultrasounds, right? For example, in detecting fetus or in fetal imaging, right? So we have that as well. So we can capture pictures and images of developing fetus, right, using these sound waves, right? The waves are reflected by tissue of different densities, and it's a difference in density in these tissues that is detected, right? That allows us to see what's happening here. Alrighty, so that's another example of using sound waves, right? Another example of sound waves is, for example, in percussion instruments like steel pan. Yes, this is in the syllabus. This is very Caribbean. Wow. But yeah, so for example, we use the vibrations and resonance of these instruments, right? And a stationary wave patterns are formed on the steel pan surface. So what kind of waves are produced? Standing waves are produced, right? That gives rise to different musical notes with different harmonics, right? So we have that there. We'll also have string instruments like guitar, going back to the same examples, where we can create standing waves because guitar strings are attached at the head and at the base. So therefore, when they vibrate, you can get standing waves, as you can carefully see at the GIF if it's smooth enough, right? So you can get standing waves there as well. You know, these, and then this would not be this would be a wave along a string, all right? Another sound wave here, right? Flute, for example, as the instrument here, right? So this is now an example of the open pipe and closed pipe mechanism, right? Where we're gonna have sound waves going in and reverberating off of the walls, and when you cover different holes, it creates differences, right, in air pressure, right? So we're looking at this now. The air inside the flute will form inside the flute rather will form a standing wave with nodes and antinodes. Based off of the length of the flute and the position of the finger holes, you will get different frequencies of vibrations, which give you different sounds that correspond to different notes. And these different notes have different harmonics, right? And that is it for really an introduction to the properties of waves. Are there any questions or concerns here before